Now it's time to add damping to the equation of motion. Generally, when we talk about damping, we assume viscous damping, using the dashpot mechanism as an example. So here in figure 2, we have a dashpot, which is essentially a piston in a chamber full of oil, and this piston has small holes which allow the oil to flow through. Now at slow speeds, the oil can flow freely through those holes and doesn't require a lot of force to push the piston along. But as the speed increases, the resistance increases, and there is more force required to move that piston at a higher speed. So we can visualize the force versus velocity or speed relationship in figure 3, and we're going to idealize this as being perfectly linear. So in order to increase the velocity of the piston linearly, we need to apply a linearly increasing force. We call the slope of that line the damping coefficient, or C. So this leads us to 3 key observations. The first one is that force is proportional to velocity. Or U dot. This then leads to a linear ODE, or EOM, which is rather convenient because that's all we know how to solve right now. And it also produces a constant natural frequency, which we will call the damped natural frequency. Note that this will be slightly different in value than the natural frequency for the undamped case. So with that information, let's formulate the equation of motion. We've got the mass connected to a spring, and then we've also added a damper using this symbol here, which symbolizes the dashpot. And that dashpot has a damping coefficient C. So our free body diagram would include our usual Ku and Mu double dot, as well as a force corresponding to C times the velocity U dot. Notice that just like the other two forces, the force due to damping acts in the opposite direction of velocity. So in the end, our equation of motion comes out to M times U double dot plus C times U dot plus K times U. And for free vibration, that's going to be equal to 0. Now let's obtain the general solution for this equation. We'll start with the very same trial solution that we did before, e to the st. We'll plug that into the equation of motion to get the following. Notice that the e to the st simply divides out, and so we're left with a quadratic equation in terms of s. So solving the quadratic formula, we get the following, which simplifies to a negative c over 2m term plus or minus square root of c squared over 4m squared minus km. Now if you recall, km is the natural frequency of the undamped solution squared, so we can bring the omega n outside of the square root, and we can simplify the term inside to the following. Notice that we get this interesting term c over 2m omega n. We'll define that as the damping ratio, which we will refer to as zeta. And so the final solution for S becomes negative zeta omega n plus or minus omega n times the square root of zeta squared minus 1. A very important side note here is that using those definitions for omega n and zeta, we can rewrite the equation of motion in a more standard generic form. So starting out from the original formulation, we can divide by m, and then substituting in those definitions, we get, notice that the velocity coefficient is now 2 zeta omega n, and the displacement coefficient is omega n squared. This standard form comes in really useful when sometimes you're given a damping ratio instead of a damping coefficient. So you're given zeta instead of c. It is also really useful in observing that the equation of motion is really only dependent on two variables, zeta and omega n, not on three, m, c, and k. So the only thing that really matters is actually the ratio between c and m and k and m. So now let's get back to actually solving the equation of motion. So here we have the solution we obtained for S, but the final solution is going to depend quite heavily on what the term in the square root actually is, whether this is 0, positive, or negative. So we actually need to obtain a solution for each one of those cases. So let's start with the case that zeta is equal to 1. That would make the term in the square root equal to 0. That means we only have one solution for S, which we'll call SC, and that's equal to negative zeta omega n. This situation we call critical damping. And we define the critical damping coefficient as 2m omega n. Notice that by plugging in this coefficient, we always get a zeta equal to 1. And the solution in this case is some constant coefficient times e to the negative zeta omega nt. Since zeta is 1, it simplifies to the following. What this means in practice is that we get an exponential decay, as you see here in the plot. And in fact, the exponential decay for the critically damped case is going to be our fastest exponential decay without oscillations. So that's what it means to be critically damped. So a system that may be designed to be critically damped, for example, may be a door, right, where you want it to swing back to the closing position about as fast as possible without much oscillation. Now let's look at the case where zeta is greater than 1. In this case, we know that omega n times square root of zeta squared minus 1 is going to be greater than 0. Therefore, we have two solutions now. And in this case, one of those solutions is going to have a slower decay than the critically damped case. So the overall system, remember, the overall solution is going to be a sum of both solutions. The decay of the full solution is always going to be slower than the critically damped case, right? But it will still not oscillate. It'll simply reduce to an exponential decay, just as in the other case. So we'll get something like this. Okay? This is what we call the overdamped case. And finally, we have the case where zeta is less than 1, meaning that omega n times the square root of zeta squared minus 1 can be rewritten as I times omega n times the square root of 1 minus zeta squared. So here we have the imaginary number creeping into the solution again, and when that happens, again thinking back to Euler's formula, we know that they would be oscillations. So anytime we have imaginary numbers in our exponential, we have oscillations. This is what we'll call the underdamped case, and it will result in damped oscillations like you see in the plot here. So we'll have oscillations around 0, but because of the damping, they will converge to 0 at some point. And so this is really our most interesting case, because this is where most civil structures reside. So most civil structures are underdamped, and that's really what makes them susceptible to resonance problems. So the underdamped solution is really where we're going to focus. So let's get the general solution first, starting with S equal to negative zeta omega n plus or minus I omega n times 1 minus zeta squared. And we're going to make a new definition here as well. We're going to define the damped natural frequency as omega n times 1 minus zeta squared square rooted. That means that S is now negative zeta times omega n plus or minus I omega d. This will make it easier to write all of this out. So then our general solution is simply the combination, the linear combination of the two possible solutions here. So we assign each a generic constant coefficient, which we will solve for later. So my first S is using the plus, and my second S is using the minus. And remember that sums in the exponential term can be simplified as the product of separate exponentials. So we can simplify this further by bringing out this e to the negative zeta omega n term, and then applying Euler's formula, we can simplify this in terms of sines and cosines, which again makes it easier to visualize. Note that the coefficients will not be the same in both cases. That's why I now change them to a and b. Because the coefficients again can be imaginary numbers, potentially, I'm just lumping them all together into a and b. Now the important thing to notice here is that we have two distinct portions to this solution. The negative exponential here is going to contribute to a decay. It's essentially a decaying function. And the cosine sine term, in parentheses, that's going to contribute to our oscillations. So it's essentially like the undamped solution multiplied by a decaying exponential term. It looks like I forgot to include the t here. Of course, the decay is also in terms of time. Alright, so the last thing to do is to apply the initial conditions in order to solve for those coefficients. So let's rewrite our solution here first. This is the general solution for displacement. Now let's take the derivative of that solution to get the general solution for velocity. Note that here we have the product of two functions with respect to t, so we can apply the product rule. So we have the derivative of the first function times the second function plus the first function times the derivative of the second function. That's all we need. So now we plug in 0 to get a in terms of our initial displacement. Cosine of 0 is 1. Sine of 0 is 0. So A equals the initial displacement. And second, we plug in 0 to the expression for velocity. In that case, we get negative zeta omega n times A. Right, sine of 0 again is 0, plus B times omega d. So we substitute in u0 for A, and this simplifies to B is equal to 1 over omega d times u dot 0, our initial velocity, plus zeta omega d times our initial displacement. All right, so our final solution we simply get by taking this equation up here and plugging in the values for A and B. It's the decay term times the initial displacement times cosine omega d t plus a term with both initial velocity and initial displacement times the sine omega d term. All right, so now let's visualize that solution and compare it to the undamped structure. So in the thick solid line, we have the damped structural response. In the thin solid line, we have the undamped response. And the dotted line shows the decay term rho times E negative zeta omega nt. This is what we would call the decay envelope of the function, showing the bounds of the oscillations. And in order to get the decay envelope, you multiply the exponential decay term by rho, which is equal to simply the magnitude of the oscillatory term. And remember that A and B can be expressed in terms of the initial displacement and initial velocity. Notice that the initial displacement and initial velocity are still the same, starting point and starting slope. And we notice that there is a slight difference in the periods of oscillation between the two, right, as is shown by Tn and Td. So Tn is our undamped natural period, Td is the damped natural period. And what we will observe is that Td, the damped natural period, will always be slightly larger than Tn. How do we know that? Well, remember that omega d is equal to omega n times 1 minus zeta squared. And we know this term is always less than 1, right? Because zeta is always less than 1. And so we know then that omega d will always be greater than omega n. However, if zeta is small, somewhere around 0.1, 0.2, we can essentially treat these as approximately equal. They will be very close, just like in this case. This is a lightly damped system, very small differences between the two. So we can say that these are approximately equal for zeta less than 0.2. Notice that when we square 0.2, we get a very small value, so this term under the square root is going to be very close to 1. Now, let's actually look at this from a different perspective by eliminating the contribution of the natural period or the natural frequency and focusing only on damping. We do that by essentially dividing the time scale by the damped natural period. So this should be actually Td and not Tn. But by doing that, we essentially express the time scale in terms of numbers of cycles. So the cool thing here is that if we express the response in terms of number of cycles, then the damping will fully determine how many oscillations it takes to get to 0. So here we have an example of 2% damping, and we see that we have well over 20 oscillations before we get to 0. Then at 5, we have about 10 or so before it effectively reaches 0. At 10, we're down to about 5. And then at 20% damping, we're down to about 3 oscillations. And this is regardless of the natural frequency of the system. What the natural frequency will do is it will stretch these or compress these over more or less time. But damping will fix the number of cycles it takes to get down to 0. Now in practice, there usually is no way to measure damping directly like we can do with stiffness and mass. It's quite an elusive parameter. And so the best way to do that we have is to get the system into free vibration and then simply observe the decay and try to quantify what the zeta is, what the damping ratio is. And one way to do that, at least with single degree of freedom systems, is the logarithmic decrement technique. All we do is simply look at successive points in the decay, and they can be at any point in the response as long as they are one period apart. But usually we will pick the peak of each oscillation. And so because we know that the decay is exponential, then we know that the log of the ratios between these points should be linearly related. So if we can establish what the log ratio is, then we can establish what theta is. So we start by defining a value delta, which is the log ratio between successive peaks. Notice here that we are using acceleration because that's the most commonly measured response through the use of accelerometers. But you could use any response. You could use the displacement response, the velocity response as well. So delta is defined as the ratio, the log ratio between successive peaks in the response. We can also define delta as a ratio between any two peaks by essentially taking an average. So if I look at the ratio between ui or u double dot I and u double dot I plus j, then I simply divide that number by j. So if I'm looking at the difference between, or the ratio between u double dot 1 and u double dot 5, then I simply divide that ratio by 4. Again, the idea here is that the log of these ratios, since it's an exponential curve, is linear. So if we were to plug in the values for u double dot I and u double dot I plus 1 into this equation, we would get the following expression for zeta. It's a little too much work to go through this derivation, but if you're interested in where this comes from, you can look in the Chopra textbook to see how this is obtained. So this is the general expression for zeta. So if we know delta, we can plug delta in and get zeta. If the damping is low, this can be simplified even further to delta over 2 pi. Right? And again, when I say if damping is low, I'm talking about zeta less than or equal to about 0.2. Okay? So the second equation here comes in handy if we know zeta but need to solve for delta. It's a lot easier to solve that way. And this is just a plot that actually shows this approximation at work. So we have the damping ratio versus the logarithmic decrement delta. And here's delta expressed in terms of theta exactly. And here's our approximation, delta equal to 2 pi times zeta. So you can see that right up to about 0.2, both are roughly linear. And then the true delta diverges from the approximation. So as long as damping is low, we can use that direct relationship between delta and zeta. And the last important thing to mention here is how we look at energy once we add damping into the system. So at time 0, at the start, our total energy will be dependent on the initial displacement, which determines the potential energy stored in the spring, and the initial velocity, which determines the kinetic energy of the system. And then generally, at any other time, we can again express the potential and kinetic energy in the same way. So in case this is not very clear, this would be the kinetic energy, and this would be the potential energy. Now for undamped free vibration, we can simply plug in the equations for displacement and velocity. So this is our velocity equation, u dot of t. And this is the displacement equation, u of t. And again, obtain what we would expect, that the energy remains constant, right? So the energy at the input is the same as the energy at any other point in the system, right? That makes sense. Energy is conserved. It simply goes back and forth between kinetic and potential energy. When we introduce damping, we actually start to dissipate energy. So that condition is no longer preserved. In fact, as time goes on, we dissipate more and more energy. So damping energy is related to the integral of the force of the damping over displacement. We can express this in terms of time as the integral from 0 to some time, t, of c times u dot squared of tau d tau. So at any point in time, this would be the total amount of energy dissipated by the damper. What does that look like? Well, we can essentially plot energy here, where the green is damping energy, or ED. The red is potential energy, PE, or EK, the energy associated with the spring. And the blue is kinetic energy, or EM, the energy associated with the mass. So as you can see, at the beginning we start out with some mix of potential and kinetic energy, right, depending on the ratio of initial displacement versus initial velocity. But quickly these start to decay over time, right, as the damping energy increases. So the energy dissipated by damping in green increases over time as the overall sum of kinetic and potential energy decreases.